everyone, Ethan here. Today I'm going to talk about diagnostic likelihood ratios. You might be wondering, Ethan, why should I care about this? Let me posit a hypothetical scenario to you. Let's say tomorrow you turn on the news, you go on Twitter, CDC has a new alert, a disease is on the loose. It's called ethanitis. Signs and symptoms: extremely questionable decision-making and judgment, childish noises of humor, distinct lack of athleticism, and a constant desire to wear blue clothes. They provide a case study of someone affected by the disease, shown on the right here, figure 1. It's got all the symptoms. Everything, oh boy, I mean, okay, I don't really care. These symptoms don't sound too bad. I mean, lack of athleticism, oh well. And then they say, ethanitis has a 50% fatality rate if not treated in the first 30 days since symptom onset. You go, And why do I say Because, well, let's think. If I'm a doctor, which I'm not yet, good news for you all, this is very concerning because these symptoms are non-specific. A lot of people make bad decisions, make dumb jokes, aren't very athletic and like color blue. And if I'm not able to identify people who have the disease, then this is a very dangerous disease. They may die. So what do doctors turn to? They turn to diagnostic testing. And we know this through COVID, but it's bigger than infectious disease. Diagnostic testing helps us screen for, detect, rule out, and monitor diseases that range from cancer to diabetes to internal bleeding. And these really guide treatment decisions because if you're able to figure out, these tests help doctors figure out what the problem is and thereby what they should do about it. And because these tests are so important, as a result, their quality, their accuracy, all of that is also extremely important. And that brings me today to diagnostic likelihood ratios. What am I going to talk about? Brief overview of sensitivity and specificity that underlies these likelihood ratios. Then I'm going to explain and analyze diagnostic likelihood ratios with positive and negative, and then compare and contrast these ratios against sensitivity and specificity. Let's get into it talking about sensitivity. It's essentially the ability of a test to correctly identify people with disease. True positives, mathematically, true positives over all with the disease. So let's say, again, you've got this population of all the people in this sample have a certain disease. Your sensitivity is your ability to label all those positives, right? It's true positives over true positives plus false negatives. What's a false negative? It's someone who tests negative but actually has the disease. So a more sensitive test is able to capture, by labeling as positives, a higher proportion of the sample that actually has the disease. Given that we're testing people who actually have disease. Specificity here is the ability of a test to correctly identify people who do not have a disease. So again, assuming that our denominator, our sample size is everyone without a disease, the specificity is the ability to sort of get the true negatives, label as negative all the people who don't have a disease. A true negative over true negative plus false positive, because a false positive is someone who the test label is positive, but again, doesn't actually have the disease. That's sort of how this probability is calculated. So again, it's sort of a way of thinking about it. I think about it is like sensitivity and specificity are assuming you're in a population of someone who all has disease and all don't have the disease. And these pure numbers can be thought of as how many of those individuals are we able to capture. However, in real life, our samples aren't entirely with disease and without disease, right? It's a lot more messy. In reality, there's often a trade-off. And I think this graph helps illustrate these concepts a little bit better when it pertains to real life, right? So this red hump here is everyone with the disease. This green hump is everyone without a disease. And these are two tests with 100% sensitivity and 100% specificity. And with this intermediate, this middle line shows how in reality, things can get a bit fuzzy when it comes to test results, right? That a lot of times people can have these sort of results that kind of, at the border of negative and positive on a test. And not at the border, but sort of overlapping, right? Some people can have a certain test result and have a disease. Some people have a certain test result and not have a disease, right? When it comes to certain numbers. So where you draw that cutoff matters. If you draw the cutoff at A, right, you will have a perfectly sensitive test. You will capture and label as positive everyone who has a disease. However, you're also going to label as positive a ton of people who do not have the disease. That's the downside of a very, very sensitive test. Usually you trade off the specificity. And the corollary is true when you talk about a specific test, right? This test with 100% specificity, this B line here, yes, you're labeling as negative everyone who doesn't have the disease, assuming that you say, to the left is everyone who doesn't have the disease. But unfortunately, right, you're also going to label as negative a lot of people who actually have the disease. You're going to get a lot of false negatives. So that may not have been the clearest idea, but in short, usually there's a trade-off between sensitivity and specificity. Sensitivity is talking about your ability to capture and label as positive people who have the disease. Specificity is your ability to capture and label as negative people who don't have the disease. And usually there's a trade-off between the two. That's that. Moving forward, what I hope this illustrates, though, what I hope these sort of figures, perfectly sensitive and person-specific tests illustrate, is that either one alone is simply not enough. Why does this matter? Let me posit a hypothetical scenario to you. Let's say you have a test for ethinitis, right? Back to ethinitis, the test for ethinitis that has very high sensitivity, and you get a positive result on this test. You might think, oh my goodness, I tested positive. I have ethinitis. This is a very sensitive test. But think about it. What does a sensitive test really tell you? All you know is a sensitive test means that your test catches all the people who have the disease and labels them as positive. But you don't know whether or not you got a false positive. That's really important, right? If you got a false positive, you got a positive result, you didn't have the disease. So you don't need treatment, you don't need anything. You're chilling. Let's ignore all of that and let's give you another scenario. Let's say you have a test with very high specificity. You test negative for ethinitis. You're jumping for joy. I don't have ethinitis. Hold up, right? A highly specific test just means your label is negative. Most or all the people who don't have the disease. We don't know about the amount of false negatives, right? We don't know about how many people test negative but actually have the disease. And that matters clinically because, you get a false negative, you don't get treatment, but you have the disease, you're in trouble. The reality is from a clinical perspective, once you get a result, you really care most about whether the result is false or not. You don't care as much about that in isolation. A test is very sensitive after you get a positive test because false negatives, which is what sort of the sensitivity is testing for, sensitivity sort of illustrates, it's sort of showing these false negatives aren't as relevant as whether or not your positive is false or true after you receive a positive result. So that sort of brings me directly to talking about positive likelihood ratios. A positive likelihood ratio is the ratio of the probability, the probability you get a true positive divided by the probability you get a false positive. So this sort of gets right at what I was talking about before, right? You get a positive result. How well can we trust this result actually means you have the disease? The way to think about mathematically is the ratio of sensitivity over 1 minus specificity. How is that the case? How do we go from here to here? Let's remind ourselves what sensitivity and specificity are. Sensitivity is the probability of getting true positives, right? Essentially, it's the ability to get true positives, your ability to capture everyone who has a disease. It's your probability of getting true positives, right? Capturing everyone who has a disease. So that's sensitivity, probability of getting true positive. However, when we try to get the probability of getting a false positive, that's going to be 1 minus specificity, because specificity is your probability of getting a true negative. The only other option in a population of people who don't actually have the disease is a false positive, right? Assuming that, again, this denominator is everyone who doesn't have the disease, true negatives and false positives. Specificity is one option, getting a true negative. The other option that a test can give you is a positive. But if our population for sure doesn't have any disease, then that positive will be false. So if your other option is positive, is false positive, to find the probability of getting a false positive, you do 1 minus specificity, because specificity is probably getting a true negative, right? And for the reason why it's 1 minus, just think about a die, right? You roll 1 on a die. What's the probability of getting rolling 1 on a die? 1 over 6. What's the probability of not getting a 1? It's 1 minus 1 over 6, right? 2, 3, 4, 5, 6, 5 over 6. And it's the same thing when it comes to specificity and its relation to false positive rate. There's only really 2 options when you have a population that doesn't have disease. You're either going to get a true negative or you're going to get a false positive, right? So in order to get the probability of false positive, you do 1 minus the specificity or the probability of getting a true negative. A little circular, but hopefully that makes sense. In short, positive likelihood ratios allow you to get a sense of what a positive test result actually means for an individual, right? If you get a positive, how much can we trust this test? That actually means you have the disease. And a higher PLR is generally good because it means that it's more likely that a positive result actually means a person has disease. Look at the math. This makes sense. If you have a high PLR, it means that this probability up top is bigger than the denominator, which means that the probability of a true positive is bigger than the probability of a false positive. So that means that, it's more likely that your positive is true. Again, I'm just repeating myself, but hopefully in repeating myself, this idea is clear. Moving forth to negative likelihood ratio. Negative likelihood ratios provide insight on whether a negative actually means a patient doesn't have the disease. And a lower negative likelihood ratio means that the negative result is more likely to indicate a person doesn't have a disease. A little confusing. Let's go into the numbers, right? If we're trying to figure out whether a negative, it's okay. The problem here is that lower is better when it comes to negative likelihood ratios. The lower the NLR is the more accurate. And that makes sense when you go into the math, right? If we want a lower quotient here, we want a smaller fraction here, we want the probability of true negative, the denominator, to be bigger than the numerator, which means, again, the negative result is more likely than not to be true, right? So that's why this NLR is better, because if we want a smaller NLR, that means that we want a higher probability of true negatives compared to a probability of a false negative. Hopefully that sort of makes sense. And how do we get that mathematically? It goes back to the same 1 minus idea. So given that we know, if we want to find the probability of true negative, how do we find that? That's essentially what specificity is. And if you want the probability of false negative, it's 1 minus sensitivity, because sensitivity gives you true positives. If we want to find the sort of the opposite of a true positive, which is a false negative, we do 1 minus that to find the probability of the opposite of a true positive, which would be the probability of a false negative. A lot of circular explanation. One thing I do want to explain before sort of condensing this down to something that's a little more intelligible. Why did we flip it? Why is the 1 minus term on the top here when it was on the bottom before? The reason why we flipped it is because of how we utilize likelihood ratio. So this is a little past the scope of this video. I've already talked for long enough, but you have to understand that all likelihood ratios are multiplied by pre-test odds to find out post-test odds and probabilities. So in short, you multiply the likelihood ratio, positive or negative, by the odds you have the disease before the test to find the odds you have the disease after the given test result. So let's say this person has certain chance of having ethinitis. You get a positive negative result. What are the odds that person has ethinitis given your positive or negative result? And this intuitively makes sense as to why we sort of flipped this when it comes to negative likelihood ratios. Because if you had a certain odds of having a disease and you got a negative test result, your odds of having a disease after the negative test result should be lower, given that that negative test result is accurate and is believable. So if we're multiplying something and we want the result to be smaller, we better be multiplying by a smaller number, right? So a more accurate test with a lower NLR means a lower final probability of disease, which is how we do this here. This is, again, important to know, but a bit outside the scope of this video. You can read more about this if you like. I'll provide some links in the description, but that's sort of why we flipped it. And it sort of explains why lower is better when it comes to negative likelihood ratios and why we flipped this 1 minus term compared to the positive likelihood ratio where bigger is better. So that was confusing. That was a lot of explanation. If you're just saying, Ethan, what the heck is going on? How do we think about this? If you have a positive likelihood ratio of 20, that means that true positives outnumber false positives by 20 to 1. So this means you can have some confidence that if you get a positive result from a test that has a PLR of 20, then okay, it's pretty likely compared to not likely that this person actually has the disease, right? These true positives outnumber false positives by 21. However, negative likelihood ratio of 0.05 means that true negatives outnumber false negatives by 20 to 1. So for every false negative, you have 20 true negatives. That means that if you get a negative result, you can have some level of confidence that this actually means you don't have the disease, given this negative likelihood ratio and a negative test result. So as sort of review, comparing and contrasting everything, sensitivity is ability to catch all positives with no regard for false positive. Specificity is ability to catch all negatives with no regard for false negatives. PLR, positive likelihood ratio, is that given you have a positive, how confident are we this isn't a false positive and that this really means you have the disease? Negative likelihood ratio, NLR, given you have a negative test result, how confident are we this isn't a false negative? How confident are we this negative test result actually means you don't have the disease? A lot of sort of confusing explanation. I hope this review at least gives you that in really cement in your mind, and hopefully some of those more complex topics sort of make sense, if not understandable. I hope this was helpful. Here are my references. I wish you the best. Please let me know in the comments or let me know if you have any questions, suggestions, criticisms, anything. Criticisms, obviously. I know some of the explanations weren't the greatest. I wish you all the best. Take care. You have a good one. Bye-bye.